Well, hello. Today we want to talk about models and math models and using mathematics to model real life situations. This is something that's kind of neat. So many times people say, well, why do I need math? I'll never use math again, whatever. There's so much you can do with math to kind of show how things work and to build a little model that you can play with and see how things work. Okay. Um, I like to build boats. Built boats for a long time and I don't know how many, but 8 or 10 maybe. And usually before I built a real boat, I would go and build, no, I didn't build a big boat like in the back, but um, some of these other ones I have. And before I built the little, 16-foot boat or something, I would go and build a little model of it because the model told me things about how it was going to work, right? If you build a little rowboat. I got interested in houseboats for a while, and I built something similar to this. But I cut out a little guy out of paper, and I wanted to be able to sleep in it and see if it was long enough, and a couple people sit back there, and all that. A model shows you how the thing is going to work, and so it's a good thing to do. We do it in math also, but it's called a math model. You're using a formula, an equation, variables to say, if I change this, how does that change that? And um, so these are pretty important to do. This is something that people have done for a long time, but physics basically is nothing but math models. We're using what we know about how the universe works to mathematically describe that and predict what's going to happen under other circumstances. Those models aren't perfect, right? We're not there yet. We don't have a complete understanding of the universe. So things have to change from time to time. We tweak the model. We bend this and say, oh, we need a little bit more of that or less of this or something. They used to have a model that said the earth was in the center and everything went around it, right? And then we said, not the right model. We need this other model. And we fix that. So you're allowed to fix a model. It's kind of like a toy. You play with it, see if it works. And if it does, then it kind of gains a little bit more status. And people believe in it a little bit more. But sometimes you got to go back and fix things. That's okay. Um, a mathematical model is a description of a system using mathematical concepts and language. So you know that's numbers and variables and formulas and stuff. A model may help to explain a system, study the effects of different components, make predictions about behavior, all these things we've been talking about. But you're definitely using variables and constants and constraints. And we've been talking about those with what we've been doing anyway. So the easiest kind of these is what we call a direct variation model. And here they have a form y equals a x to the n. So that's the basic structure of the direct variation. A couple sections ago, we called that the power function, where you had some power of x, right? But this is thing that you see right there. The linear model would be the easiest, and this is a kind of silly example, but that's okay. Let's say that you sell ice cream in the park, and you load up your cart. You want to see how much ice cream you need to put in the cart that day. Well, you'd probably go look at the weather thing, and if it's going to be cold, you don't need a whole lot. You're not going to sell a whole lot of ice cream when it's cold. On the other hand, if the temperature goes way up here, then you need to stock up, right? Because there's some model that shows as the temperature goes up, ice cream consumption is going to go up. Okay, so that's the model there. And maybe for every rise in temperature you sell an additional four ice cream cones or something, whatever. Um, that's the direct variation. As X goes up, then y also goes up. And notice that those are both on top. Y and X are both on top. If this guy goes up, if I put a bigger X in there, I get a bigger Y, right? And so that one makes good sense. You could have a squared or a cubed on there or something, and you'd have to do some curve fitting, some graphing, and take actual data, look at a picture of it and say, oh, that's a squared, all those functions we've already been talking about. Here's a little example. Let's say you've got a lawn business and you're scattering fertilizer, and you read on the bag and it says you need to cast out 20 pounds of fertilizer for every 1,000 square feet. So, how much fertilizer do I need for 700 square feet? Well, you could set this up as a proportion, but you could also cook up a formula here, a model that would tell you every day. You could say, okay, today's lawn is 900 square feet. How many pounds of fertilizer do I need? Here's all you'd have to do. I've got F is the pounds in fertilizer, and A is the area of the lawn. And those are related. There's a direct relationship between those. The bigger the area of the lawn, the more pounds of fertilizer I need. So I'd set it up where they're both on top like that. And this K is a constant that says essentially how many pounds of fertilizer per square feet of lawn, right? So that's a constant I'm going to have to determine that. So this first bit of information that they give me here is going to allow me to find K. I'm going to take this right here and use this to find K. Well, if I'm trying to find K, I could divide both sides by A. The A's are going to cancel there. Now I've got K by itself, and I could come in here and say F, the fertilizer, is 20 pounds and A is 1,000 square feet. So that would be 20 pounds over 1,000 square feet. And that is equal to K, my constant, 20 divided by 1,000. You got to move the decimal place 1, 2, 3 times. So I get 0.02 pounds per square feet. And now I have a constant that links how much fertilizer I need for lawn. All right. The second line of this thing says, okay, on day 2, you've got a smaller lawn. So I'm going to need less than 20 pounds. How much less? I don't know. Let's take this K, put it back in my formula. Now that I know how much it takes, I can write F equals uh, 0.02 pounds per square foot times the area. And all I have to do is say, well, today I got a different amount of area. Let's put it in and see how much fertilizer I need. Interestingly enough, these units are pretty handy because see how I've got feet squared on top and feet squared on the bottom here? The feet squared on top are going to cancel the feet squared on the bottom. And the only unit left is going to be pounds. So that will, um, tell me what I need to put in my hopper. 0.02 times 700 is 14 pounds of fertilizer for that job. And I think that's kind of neat, right? Yes, we could do it with a proportion, but you'd have to build the proportion every day. Now we've got this formula right here that always works, and we don't ever have to go measure it again. Um, Here is a direct variation model with a cube, and you could do this the same way. It says the weight of a cube depends on the size of the cube times the density of the cube. So there's two things that we're multiplying, size and density. I'm going to just go with S, and let's go with a D for density. Okay. So I could build this thing. The weight is you have a bigger cube, it's going to have more weight. If there's more density, it's going to have more weight. And the only other thing I really need to do is to slip a constant in here so that I can scale the whole thing up or down to make it the right size. Also, that constant sometimes helps fix the units, but we don't need to worry about that. All right. Then they're going to give me some initial conditions. And they're going to say, well, today's box has a weight of 43 pounds, and that would be W, and the sides measure 15. We need the size. This is big S over here, the size of the box, not the side of the, if I've got 15 here and 15 here, 15 here, uh, I don't want to use 15. The volume of a cube, length times width times height. So I really need to go S cubed on that. If they're going to be giving me the side instead of the total size of it, the volume of it, then I need to get back to what they're working with. So I'm going to rewrite this. The weight is equal to the constant times little s cubed times the density of the material. Um, I think the density actually is our constant here, and apparently we're using the same thing. So let me scratch out K here. The two numbers that they're giving me are the weight and the length of the side. And it's a cube, so that's the same everywhere. That would let me essentially D is the density. Maybe we make aluminum cubes all day long, but people want different size ones, and so uh, that number is going to be the same. Okay, weird problem. Here's a W divided by S cubed. That's my density. They gave me a W 43 and they gave me an S 15, but I got to remember to cube it. And that's equal to the density of this thing. And I could get a number real quick out of that. 43 divided by 15. I'm going to cube it right here, right now. And that would be 0.0127 is my constant. That's the density. If I'm always using the same material, that's going to be the same every day and I can just use it. So uh, if you were using different metals every day, then you'd have to have that as a variable and then put in a constant, which would make life a little more tricky. You'd actually have to have two of them, two data points to find that, but blah, blah, blah. All right, watch here. I could put the units in on this. This was 43 pounds, and this was inches, which got cubed. So my unit there would be pounds per cubic inch for the density. And that makes sense because that's how much weight per little bitty cube. If I chop this thing up into little cubes, how much would each one weigh? Okay. Now that I have that number, I want to take that and put that back into my formula so that I can use it the next day. And I'm going to come up here and let's go to right there. All right. That tells me that the weight is equal to, I could put that constant out front, 0.0127 pounds per cubic inch. And I want to multiply that by S cubed. So that is my general formula. And we're ready to go now. They're saying, okay, hey, Joe, make one that's 12 inches on the side. Tell me what the weight's going to be so we can calculate the shipping on this thing. And you go, okay, I got a formula for that. The weight is going to be equal to 0.0127 pounds per cubic inch times S. You said 12 inches, right? Yep, 12 inches. Don't forget to cube it because the formula says so. And you do all that. And 0.0127 times 12 cubed. And that'd be 21.9456. Let's just go with something like 21.9 there. I think it's good enough for what we're doing. Okay. Good enough for the postal people. They'll figure it out. All right. But that is, another direct variation. I got something called the inverse variation here. And with an inverse variation, it's inverted. And we've seen the inverse function, so it looks kind of like that. And this is no different. Right here, as one variable goes up, the other variable goes down. Okay. Thinking about our ice cream, remember, the hotter it gets, the more ice cream you sell. Well, what about mittens or winter hats? You know, when it's January I can sell winter hats all day long. Give me all you got. But over here it's July or something. Nobody's wanting a winter hat. It's going to go down. And there's a function that describes that graph right there. And I could say, well, what if it's March? You know, in March I need about this many in my cart. Okay. And it's going to vary day to day and stuff. But this is a model to say, give me an idea of what I need today. All right. The difference with this one is the X isn't on top, it's on the bottom. It might be even clearer to write Y equals 4 over X. Whenever you have this inverse function, you want to put let me get that calculator out of the way there. Sorry, I got two screens. So, um, whenever you have an inverse function, the variable is on the bottom. It's inverted, if you will. So here you've got this structure y equals some constant a, k, whatever you want to call it, divided by a power of x. And we're just doing the one where the power is 1, but that's okay. This is a handy model too. Here's an example. The time taken for a water heater to boil water is inversely proportional to the power of the water heater. And then they're gonna give me some information about this thing right there. So let's write out our variables, see what we've got. They're saying that the power equals 2,000 watts, and the time, I guess we're using a big T, is equal to 240 seconds. So, you know, as soon as I see it's inversely proportional, I know the time is inversely proportional. It's upside down. P is on the bottom down there. And we're ready to go. I want to solve this thing for K and plug in my numbers. So I'm going to multiply both sides by P to cancel that P on the bottom. And I'll have T times P equals K. I've got a T, I got a P, so we're going to drop those in. And the time here was 240 seconds, and the power was 2,000 watts. And that's going to give us this constant that tells us how good our water heater works. And that's going to be, you know, true every day until the element goes bad or until I have a electrical brownout or something changes that wasn't predicted, wasn't built into my model. But 480,000 is that number right there. All right. So I've got my constant now, and I keep forgetting which screen I'm on. So sorry about that. Um, Next up, they've got this other information. So, okay, now we're going to turn the power down. It's not going to be that much. I need to know how long it's going to take. I say, great, I got a formula. The formula is T, the power, I'm sorry, the time equals my constant. Just figured out that was 480,000 and divide that by the power. Okay. Whenever you get this K, you just want to take it back to the original formula and plug it in right there. So in our case, how much time will it take? Well, I got a 480,000 on top, and today I'm only using 1,000 watts, and I divide by 1,000, and I get 480 seconds. Okay, so that's an inverse variation there. Again, it could be a squared or a cubed on the bottom or something, but when one goes up and the other one goes down, you need that variable on the bottom. And you know, if those constants, if the numbers are, you know, that would be the formula right there. And when P goes up, bigger number, you're dividing by a bigger number, that's going to give you a smaller answer right there. So sometimes you have both of these at the same time, and I don't want to belabor this, but here's a hot thing and here's a cold thing, and they are connected right there. Maybe it's a piece of glass, sun shining on the outside, and it's nice and cool inside in the summer, and you've got heat moving through that glass, and you want to know how fast it's going to take for that heat to come in here. Well, there's a formula from that. This is from physics. Of course, Q is the heat, T is the time. You've got this constant thermal conductivity. Is it made out of aluminum or glass or wood or steel? These things conduct heat at different rates, right? How big is the window? If I had a really big window, more heat would move through that, right? A little bitty window wouldn't carry as much. The thickness of that window right there, how far does it have to move to get to me? That makes a difference. So you got a formula there, but check it out. If A gets bigger, that's on top. That's a direct variation. And when the something on the top gets bigger, then your answer gets bigger. That's direct. What am I trying to write? Direct. Okay. On the other hand, if I put this number right here, if that thickness of the glass gets bigger, that's going to slow the heat down and it's going to make the answer smaller. Okay. So that would be an inverse variation. And in this problem, if the area gets bigger, the answer gets bigger. If the change of temperature gets bigger, that's going to make heat move faster through there. But if the thickness of the glass or whatever this material is bigger, that's going to slow it down. So you can have both of them at the same time. Here's one more where it's got stuff on top and the bottom. If I take the sun and the earth, or any two objects that have mass, this could be a banana and a paper clip. Okay, it doesn't matter what the two things are. You take the mass of the first one and the mass of the second one and the distance between them, then there is a formula that says how much force, how much gravitational force is between those. And, when you look at it like that, it's a pretty straightforward, simple thing that we do in physics. We're building these models, these formulas to say, how does that work? Well, if the sun all of a sudden doubled in size and mass, somehow I can't do that, but whatever, you'd put a two right there, and that would make the force twice as big, right? If I doubled the distance right here, all of a sudden R got bigger, and I put a two here, the R still gets squared, but now the two gets squared too. That's a four on the bottom. I would get a factor of a fourth in there. So these variables and the powers on them determine how these things work. And you can calculate how much gravity there is. We can watch stars and watch things out in space and calculate the mass of the star by how fast it takes a little planet to go around it. We can see a little blip of light every time the planet passes in front of it and go up. There it went again. There it went again. There it went again. It's not that fast, right? But you know what I'm saying? Um, and work out the mass of Alpha Centauri, which is, I don't even know, 27 light years away or something, whatever. I don't remember the number. But so these formulas are pretty handy. Exponential growth. You put a bunch of bunnies together, then you're going to have two rabbits and three rabbits and four rabbits. It's gonna go up like that. And it's not really that it goes one, two, three, not like a linear function. It's not a straight line. This is an exponential growth. We're going to talk about exponents and logarithms before this class is over, and think about these kind of models. So I'm not going to say a whole lot about it now, but when you look at it here, if you make a little table of values, if I put in x equals 1, then 4 to the 1 would be 4. So after 1 year, I've got 4 rabbits. When I put in a 2, 4 squared would be 16. The thing is that the exponent is the variable here, and that's why they call it an exponential model or an exponential equation. You put in 3, 4 to the third would be 64. See how fast this is going up? 4 to the fourth would be 256. Um, those bunnies are, it's like stand back because they're busy, right? That's an exponential model. Don't need to say a whole lot more about that. But the form would be y equals some constant times raised to a power. I'll just put a x here like that. That would be the easiest version of that. Okay. I could have an exponential decay model when we talk about nuclei of atoms and you know fission where these things are radioactive and break apart. You can take a chunk of uranium, set it on your desk. I don't recommend this, but you could do it, and it starts off with this much radioactivity, and after a certain amount of time, it's fallen to to half of that or a quarter of that or, an eighth of that, 16th of that, a 32nd, it's going to fall off in that pattern. That's what we call exponential decay. It's kind of like another day we talked about cookies, right? And if I had a whole cookie and the first day I ate half of it, I just went from one down to a half right here. And the next day I ate the next half. So that takes me from a half down to 0.25. And then I eat half of that. So now I'm down to an eighth of it. Every day it's dropping by a half, but theoretically, again, this asymptotically approaches radioactivity level of zero, but it never really gets there, right? We never completely run out. So that's an exponential decay. The model there would look like this: y equals e to the negative x. You just slip a negative sign in there. Maybe there's a constant out front. I shouldn't do the e. Let me not do that. Y equals, it's not wrong, but it's let's just go with this. All right, make life easy. Okay. We haven't done e yet, but we will. And so there's some number and we're raising it to a negative power. You could also write that as use up the negative part of that exponent and say 1 over a to the x, but you're going to get a graph that looks like that. Got one more exponential for you here. What if you put a bunch of fish in a tank? Well, there's only so much oxygen, right? You got O2 floating around, and when there's not enough oxygen, the fish stop growing, right? They'll die off, and then you'll be at a level where they can maintain. There's only so much food in there. There's only so much, natural resources are kind of limited. How much gasoline do we have left on the planet? We've used a bunch of it. We're not done yet, but we will get there at some point. And there's only so much we can use. It kind of levels off, right? Our use of gasoline cannot go up and up and up forever. The number of fish that we can put in a tank has a natural limit, and it approaches that limit. And there's just all kind of models. It's going to look something like that. I'll write y equals 1 minus some number to a negative power like that. That's the thing that we do. You can even think about this in terms of your homework or cleaning your room or whatever. Um, let's say here's 100% job that you could possibly do, the best you could clean your room right there. And after a certain amount of time, you've cleaned up to 78% of it. Well, if you spend that same amount of time again, it doesn't go up to 156 or whatever, you know, there's not that much left to clean. It's harder to clean that second chunk of room up. And that's why you put it off. But you can only go to 100%, right? There's the maximum. That's the best job anybody could do. And a third hour, or whatever the time unit is here, doesn't move you way up. You are approaching that maximum cleanliness of your room, but you have diminishing returns here. And same thing works with your homework. If you spend 3 months in this class, if you spent 3 years in this class, you're not going to learn, uh, you know, what would that be? 12 times as much algebra. There's a diminishing return, and you'd move on to calculus or something else to instead because you've got what you need out of it. So that's an interesting function right there. Uh, at the end of this class, we're going to talk about simultaneous equations. So sometimes models have more than one equation. If they have two or more equations, then maybe one function looks like this and the other function looks like this. And we want a solution for both of those, which would be that point right there. So we'd be looking for that point. A lot of times you see the supply and demand curve in business, and let's say you're selling something. I don't remember which way the graph goes. I think it's this way. Supply goes up, demand. Let's put demand in. I don't remember. I'm not a business person, but let's say you're selling I don't know, pine cones. You're here in South Carolina and there's a ton of pine cones, right? So the supply is really high and the demand is going to be really low. If, on the other hand, if you're selling gold bars, the supply of those is really low, but the demand is really high. So you're going to get a curve like that. On the other hand, you've got the other function that says, you know, um, the more of these I have, if I have a higher supply, then bad example. Um, but you get an idea. There's a price here where you should set your price, you know, for dishwashers or pine cones, whatever you have. If you price it too high, then you're not going to get your, you're not going to be able to sell them. And if the demand goes crazy all of a sudden, like toilet paper during COVID, right? Um, people were gouging. They go buy all the toilet paper and sell it on marketplace or something. Um, anyway, maybe you've got two simultaneous equations here. You're looking for something that makes both of those happy. And we will do that. You can do it a whole bunch of ways. You can build a matrix substitution method. We're going to go through all these, so don't worry too much about that right now. But that's an interesting model. We're not going to do this. It's in your book because you have, I think, 3 or 4 chapters on trigonometry in your book, and you're welcome to look in there. But this would be a sine function, and it goes up, and it goes down, and it goes back up. This could represent the temperature over a year, you know? Maybe here in March it's kind of in the middle, and July it goes up, September goes back down, and January is really cold, you know, and the temperature is following a line like that. Maybe it's a spring that's bouncing up and down. You put a spring on the table, you put a little weight up here, and you push it down and turn loose, and it's just going to bounce up and down. And if you kind of mark that out in time, it goes up, it goes down, it goes up. A pendulum, turn it loose, it's going to go back and forth over there. And you could graph that thing, how far away from the center line it is. It goes back and forth and back and forth. Radio waves, golly, just all sorts of things that we use these sines and cosines. And that's trigonometry. Good stuff. Not what we're trying to do today. Here's one more just for kicks. You could have a differential equation model. This is after you do calculus, you learn about some differential equations. So this is way down the line out there. But if you jump out of an airplane, gravity is going to pull down on you. And meanwhile, air resistance is going to slow you down. And at some point, you reach what's called terminal velocity, where these two forces cancel out and you're no longer speeding up, you're no longer accelerating. And you can build that formula right here. Sum of the forces equal the mass times the acceleration. And you get this. The trick is that the velocity is tied up with your acceleration right there. It's the derivative. Well, the acceleration is the derivative of the velocity. That's a differential equation. That's a kick in the seat of the pants because now you can solve some problems that are really pretty involved. Um, there's the formula for drag. You don't need to know that. All right. I don't even know why I put that in there. Y varies directly as the cube root of x. And when x equals 27, y equals 15. Let's do these two and we'll be done real quick. All I have to do is see that this is a direct variation where this one is jointly and inversely. Jointly is a word for directly. Okay, but that's what you're looking for. How do these things work? Right here, all I have to do is say y varies directly. So I know that there's the cube root of x. So I want that in there. There's the cube root of x. And it doesn't equal it, it varies with it. So that's where I put in that constant. Call it a, call it k, whatever you want to call it. But slip a number in there like that. And now y is tied up with the cube root of x, and I've got that constant to scale it and maybe fix the units and stuff. And then they give me a data point here. So I know that I can put that in, and I don't know why I wrote y there. Y is 15. Here's a. I want the cube root of 27. Let's go ahead and simplify the cube root of 27. That would be a 3. And I could divide by 3, and I'd get a equals 5. I use that first bit of data to figure out what my constant is, and I put it back into the formula. And now I know that y equals 5 times the cube root of x. And so then they would give me another data point. Well, today, if x equals 30, get busy. Tell me what y is going to be. And you could do it. You just drop the 30 in right there, take cube root, multiply by 5, and you got your answer. Okay. Over here, this one's interesting. This one has y varies directly as x, or jointly means, that x is on top, the z is on top. So I've got three variables here. The W is inversely, so it's on the bottom. And I've got an X on top and a Z on top and a W on the bottom. And I got to toss a constant in there to scale it. And then they give me an X and a Z and a W and a Y. That's everything except for A. So I could come in here and say, great, I got everything I need. I can use that to, I'm sorry, this is supposed to be a 6. Okay. Um, I solve for A. I put that back into the formula. Here I'd have 15. 6, that'd be 60 divided by 15 would be a 4 for A. Okay. I can put that back into the formula. Now I got a formula y equals 4xz divided by W. And they give me a new set of numbers. On Tuesday, the boss says, what if x is z and x is 4 and z is 9 and w is 15? And go, got it, boss. Right. So it's pretty handy. It's pretty good. Physics and business and economics and chemistry and anything with numbers and where you're trying to understand how things work. Uh, this is pretty good stuff. That's all I got. Thanks for listening.